Hi, this is the very abbreviated version of Lecture 3, pre-class video. The first two were quite lengthy and it seemed like they were way inappropriate. So what are we going to talk about? We're going to talk about the normal curve. Things to know about the normal curve are that it's theoretical, that every normal curve will be divided into quantifiable chunks, uniform chunks, where one standard deviation from the mean will account for 34.13% of the data from the mean to one standard deviation, 34.13% of the data on the other side. If you go 2 standard deviations, you will capture 95.5% of the data in every stinking normal curve in the world. If you only go 1.96 standard deviation units out, you'll catch 95% of the data. That's really important for a lot of other stuff. People report data using z-scores. And z-scores are nothing more than an attempt to tell me how far away from the mean in standard deviation units is my score. So if the mean is 100, standard deviation is 25. If I got 125, that means I'm 1 standard deviation above the mean. If my score was 75, that would tell me that my score was 1 standard deviation below the mean. We won't spend any time in this video on the distribution of sample means, except only to say that that's a cool hypothetical thing too. If you take samples of much greater than 120, or greater than or equal to 120, big samples from any large population of data, doesn't matter how the data is originally distributed, but if you take big samples from any big population and you distribute and you plot only the means, the distribution of sample means will be a normal curve. Always. It is. And it will have, because it's a normal curve, it will have all those appropriate matching points. 34.13% of those means that are calculated in or plotted in the distribution of sample means will be between the mean, the grand mean, and 1 standard deviation away. 34% on either side, yada, 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 yada. If the sample size is big, then you have this distribution of sample means, and by definition, and to confuse people in a biostats course, for this hypothetical distribution of sample means, when you move 1 standard deviation unit in that distribution of sample means, that is what's called the standard error of the mean for this hypothetical distribution of sample means. Oh, isn't that a crazy thing? Standard deviation is equal to the standard error of the mean. But the reality is that's only true in the la-la land of the hypothetical perfect normal curve and the hypothetical distribution of sample means. Nobody actually does the process of calculating multiple means from the population and creating a distribution of sample means. Instead, they estimate the standard error of the mean by taking the standard deviation and dividing it by the square root of the sample size, square root of n. That is essentially the way to estimate the standard error of the mean. So when you take and you get a single sample, you calculate the standard deviation from a calculator or a computer, and from that and the sample size you calculate a standard error of the mean. You are in essence saying, if I had taken multiple samples of large size from this original population, and if I had plotted those sample means in a distribution of sample means, by golly, the standard deviation of this whole distribution of sample means would have been equal to, bingo, the estimated standard error that I made from a single population, from a single sample. That's why people calculate a standard error of the mean, essentially to estimate what would be the standard deviation of the distribution of population means, of sample means from the population. So why is that important? It's important because what we're trying to do is, from a sample, we're trying to estimate the population mean. A sample mean is a single point, which is only sort of a good starting point, really. What you really want is a range of values And the best range of values, the most commonly used range of values, is a confidence interval or a confidence limit, if you will. And all that is the confidence limit is simply that range of values that you say, well, I am 95% confident that the true population mean is within this interval. And this interval is, of course, centered on my sample mean. And the range is based upon, you got it, the standard error of the mean. And so we need to calculate the standard error of the mean in order to get a confidence interval. And we know that we could get the standard error of the mean if we took hundreds upon hundreds of huge samples and plotted a distribution of sample means, but we don't want to do that. Nobody wants to do that. So what do? You take a single sample, larger than 125 or so. From that sample, calculate the variance, sum of the squared deviations from the mean divided by n minus 1 because it's a sample. Take that variance value, take the square root of it, and that is by definition the standard deviation. Take the standard deviation, divide it by the square root of the sample size because that's the mathematical formula for estimating the standard error of the mean. Standard deviation divided by square root of n. When you have that standard error value, then you have essentially what would be, if you ever did it, the standard deviation of the distribution of sample mean values. And so then you say, oh, I'm going to build a normal curve around my sample mean using my sample standard error as the standard deviation of the estimated distribution of sample means. And so then if you go out 1.96 times the standard error of the mean, you've essentially moved out 1.96 units in standard deviation units on a normal curve. And so now you have the window, which is your 95% confidence interval. And so for a single sample of large size, the 95% confidence interval is essentially equal to the standard error of the mean that you estimated from your sample size and your sample standard deviation times 1.96. So you go 1.96 above the mean of the sample, 1.96 below the mean of the sample, and you say, aha, I have a 95% confidence interval. I am 95% confident that the population mean is in this window. Still not certain, but I'm 95% confident. So that's if the sample mean is big. 120, 130, I think 128 is the official cutoff in most textbooks, but really about 120. Why is there a cutoff? There's a cutoff because the distribution of sample means, which is the foundational hypothetical piece for doing confidence intervals, the distribution of sample means is quite different if the sample size is smaller than 120. As you go from 120 to 50 to 10 to 5, the distribution of sample means is no longer a normal curve. It's only a normal curve if the sample size is big. If the sample size is 50, it's kind of normal looking, but it's a little shorter than normal, and it's got a little bit more out on the edges, a little fatter and flatter. And if the sample size is 25, it's even a little bit shorter, a little bit fatter, a little bit flatter. If the sample size is 10, this is a really fatter and flatter distribution. Those are called t-distributions. And they're made famous by Gossett, who wrote under the synonym of student. But that's another story. But essentially, if the distribution of sample means is no longer a perfect little normal curve, and there's more and more of the data stuck out on the edges, then if you want to capture the 95% confidence interval, you got to stretch that interval wider and wider as you go to smaller and smaller sample sizes, because more and more of the sample means in the theoretical distribution of sample means end up out there in no man's land in the wings. And so now, how do you do that? There's a whole table called a t-table. It's also used for analyzing t-tests, but basically for this exercise, it's the t-table for telling you 4 t-distributions of different degrees of freedom, which really translates to of different sample sizes. For the t-distribution of different sample sizes, instead of 1.96, what is your multiplier? Is it 2.201? Is it 2.5? Is it 3? But as you go from a sample size of 130 or 128 down to 50, down to 30, down to 10, down to 5, the value of the t goes from 1.96 to 2 to 2.3 to 2.5, maybe to 3 and 3.5 and even 5. As the degrees of freedom get smaller and smaller, because you have to make your confidence interval wider and wider and wider in order to be sure that you really have a 95% chance of capturing the true population mean.